Now let's look at the effect on genotype frequencies and allele frequencies of mutation, migration, and drift in the context of the Hardy-Weinberg assumptions. So first of all, the effect of mutation, and I've put up here a little spreadsheet showing the effect of mutation on allele frequencies, where the starting allele frequency is 1 and 0 for two alleles, and we're looking at the appearance of allele A2 progressively as time goes by. And we're looking at a mutation frequency here, shown by the column in yellow, of 1 in 1,000. So mutations can enact, in this case, we're assuming can activate a gene at a finite rate, mu, which here I've given 1 in 1,000, but that's very high. And I'm making the assumption that the rate of back mutation back to the wild-type condition is negligible, and therefore the change in allele frequency from one generation to the next is equal to the allele frequency in the first generation minus the mutation rate times its frequency. Now, the effect of mutation rates on allele frequency changes are really quite small, as you can see from this graph, and that's when the mutation rate is 1 in 1,000 per generation, and that's not really realistic at all. So, for example, for cystic fibrosis gene, we know that the mutation rate is roughly 1 in 3 million per generation. So we can, over short time spans, more or less neglect the effect of mutation in evolution changes. But obviously, over long time spans, it's the raw material we need to generate those alleles that the other things can act on. Now, in the last few modules, we've looked at the effect of selection on allele frequency. Now let's have a look at drift. Here's our favourite population of individuals in Genesville, and you can see that it's not an infinite population. It's a finite population. Its allele frequencies at the starting point are equal. It has two alleles or one locus, and they're both present at equal frequencies. They're 0.5. And although it's a small population, we can take a small sample from it to produce our second generation. So we're going to neglect all the individuals that weren't included in that sampling and simply count up the frequency of alleles in our sample. And by chance, we placed our loop around part of the population, which gives us an allele frequency for allele A1 of 80% in the next generation, compared with 50% in the first generation. If we placed the sample somewhere else, we might have gone in the other direction. Now, drift is a random sampling process, and so can't be analysed through standard predictable equations, but it can be simulated by computers, and here I'm showing you some snapshots from some simulations that are run on the Hulsinger Lab website at the University of Connecticut, which you can go away and run for yourself. And here again we have, just as we had with my previous simulations, the effect on allele frequencies over 100 generations, this time run multiple times. And in this case, we're looking at a finite but large population, a population of 250 individuals, running that otherwise the Hardy-Weinberg equation through, but with a stochastic sampling variation going on. And you can see that instead of having straightforward horizontal lines where the frequencies remain exactly at 0.5 generation after generation, the lines bump around, up and down a little bit, randomly from generation to generation. If you think it's not random and you think you can see patterns, that's because your brain is always looking for patterns. Actually, those are very random events. And you can see that they gradually drift apart generation by generation instead of remaining constant. If we change a parameter of the equation to make this even smaller population, so instead of having, if we change the conditions now so that we're looking at a population of the same size, 250, but the starting allele frequencies are much lower, 0.1 in this case for allele A2, what we see is the same sort of level of drift, but the consequences for allele A2 are much more severe. In 4 of the simulation runs that have run here over 100 generations, the allele A2 has bumped down to frequency 0 just by chance, just by the action of drift. And the really important thing is that when an allele becomes eliminated from the population by drift, it can only come back into the population if it's mutated back in or if it migrates in. So the consequence of drift is particularly extreme on the fate of alleles that are at low frequency. The other really important amplifier of the effects of drift is the size of population. We were looking at a large but finite population of 250 in those previous simulations. If you reduce the population size down to 10, as in this population simulation here, and in this case we're starting with frequencies of 0.5 for both alleles, we see that the amount of sampling variation is much higher proportionately, so the frequencies are bouncing around really quite dramatically. And because the amount of bouncing around is at much greater amplitude, there's a real chance that it hit either 1 or 0. And if an allele hits 1, it becomes fixed in the population, and there's only that allele present. And for the other allele to come back, there has to be some back mutation. Or if it goes to 0, it's eliminated from the population, and to come back, it has to mutate in or migrate in. So small population sizes almost always result in the elimination of polymorphisms because of drift. In each of these cases, there's been no effect of selection at all. This has just been drift. So the effect of drift depends on the fact that each generation is a sample of the generation before. And so the small populations result in more sampling error, and that results in more drift from generation to generation of allele frequencies. We've noticed how if we move starting allele frequencies closer to 1 or closer to 0, the effect of drift increases. We've also seen how drift leads to the fixation or elimination of alleles in the population. Now, in other podules in this series on evolutionary phylogenetics, we'll see how we depend quite often on molecular clocks. And molecular clocks, in their turn, depend on the effect of drift on the frequency of alleles that have no fitness differences amongst themselves, on neutral alleles. And so drift is a really important thing. So if we wanted to summarize all this up in graphical terms, we'd start with a population, and we'll introduce a new homogeneous population. We're introducing a new allele by either migration or mutation to have a slightly heterogeneous population. That population tries to reproduce, but the next generation is a sample of that population. And drift can, as a result, eliminate the new mutations that are at low frequency, or selection might be able to grab hold of them if they have a fitness advantage and amplify them. So drift is really important, particularly in small populations, and particularly when there's not much selective advantage between the different alleles. Selection is really important in large populations and where there's significantly altered fitness. So far we've been talking about characteristics that are either or, they're qualitative characteristics. But you should bear in mind that most important variation in populations, human populations or any other animal populations, are quantitative, like, for example, variations in speed and strength. They are quantitative, they're on a continuous scale, and they may not be completely independent of each other. So if you want to look at how to handle quantitative variation, you can't use the equations we've been using so far. We have to use other methods. And to that, you can turn to the next point.